Hi guys, my name is Ricardo and we are going to see in this lecture how the database management systems DBMS handle with transactions that are concurrent and therefore try to change data items in the database at the same time. The situation is more common than we think. The DBMS handle these situations without our knowledge. But if you know, without it, it would be impossible to have multiple programs accessing the same database. Today we're going to cover the theory about the transactions, all the transactions, their properties, and the problems that arise when they interleave their execution. We will not cover at this time the whole of the concurrency control system. Later, we will discuss about this with theory and some practice examples using database systems like MySQL or PostgreSQL. Okay, so let's start. We can see here. We're starting talking about the interleaving process. The interleaving process is very important. The database systems works like an operating system. The user requests tasks or jobs to the operating system, and it will manipulate these requests by interleaving them and managing all the computer resources like printers, memory, databus, CPU, buffers, etc. In the database systems, the resources are different, but they need to manage also. And they are columns, data items, records, database, group of records, and etc. The problems that arise of misapplication of a database resource will be the same in operating system, like deadlocks and starvation problems. Therefore, it's important to understand what kind of problems we will encounter when working with transactions. Like operating system, database systems can be single user or multi-programming. The single user database are for personal use and will not handle with multiple transactions. Instead of the multi-programming database that can handle with multiple transactions by interleaving them. The transactions will be interleaved if they are a single process, like between the interval here, T1 and T2, or by parallel programming if they are multi-process, like between the interval T3 and T4 in this diagram. So we are talking about transaction, and it's normal to question what a transaction is. A transaction is considered an execution of a program or part of a program that can accomplish one or more of these operations: retrieve, delete, insert, or update data items. It becomes a unity of execution and an atomic operation in a database. There's no limit to the number of transactions submitted to a database, nor the amount of operation performed inside a transaction. The memory is the main problem. More memory, more operations, and more transactions. Every operation inside a transaction must be placed between the beginning and the end transaction common. Some transactions can alter the data in a database, but not all transactions. There are some transactions that only retrieve data to show in a table, for example, or a printed report, another report. These transactions are called read-only transactions. They cannot affect too much the database in terms of transaction control, okay? But they still have their relevance, and we're gonna see it why it's relevant. So a transaction can manipulate any data item. The kind of this data item depends on which granularity the transaction refers to. It can be a column, a disk block, for example, or a record. Although the transactions can be of different types, For us, there is only two operations that matters for the transaction manager. A read and a write operation. These operations are responsible for changing or retrieving data from disks or memory in case of main memory databases that store the value in its main memory, not in a disk. So, if the transaction writes value to an item, when will it be available for the other transactions? Because they share data. This decision is responsibility of the operating systems together with the recovery administrator. This decision affects the others transactions that wants or they may use this data. A transaction, for example, can share data by sharing their buffers, their own buffers. The buffers, it contains the changes each transaction made and the actual value of an item. To help the recovery system do a rollback in case of failure, each transaction keeps stored, for example, two sets of operations. A write set that it's a set of write operations, and a read set, it's a set of read operations. So it's important to note that these operations are used to recover a schedule in case of conflict or failure. This topic will be covered in the next screens here. Sharing data can bring some problems to the set of transaction. Imagine, for example, that you will buy a ticket for a flight and they're looking for the seats in a specific flight for the Caribbean island, for example. The system show you that the flight has only 2 seats available to be sold. But you take a long time to decide yourself to buy or not the tickets because you're talking with your wife, your husband, your mother. And during this period of your indecision, for example, another decided user accesses the system and buy the last 2 seats available in that flight. Therefore, when you decide to buy your seat, there is no more seats available to buy. But your system continues to show you 2 seats available. The DBMS encountered these problems every time the transactions are badly programmed by the programmers. In fact, there is 3 main problems that the concurrency control can face while the transactions are being submitted. So we're going to list it. The first one is the lost update. The second one is called uncommitted dependency or dirty read, the problem we mentioned about the flight ticket, and the inconsistent analysis problem. So the first one, the lost update, occurs when a transaction updates an item that has not been committed yet by another transaction. So therefore the data updated by the first transaction are lost by the second transaction when the second transaction will be committed. The second problem is called uncommitted dependency or dirty read. It is a problem that occurs when a transaction tries to read a value before it's changed by another transaction. The value read does not reflect the true value after the second transaction commit the new value. And for the last one is called the inconsistent analysis. And it occurs when the transaction needs to repeat the read of an item every time it changes. Normally, it happens using some aggregate functions like sum, average, or other aggregate functions. So, if failure happens, how the system handles with the transaction's failure. The database needs to have a plan to recover its integrity. The integrity of the BMS depends on 2 major properties that we must respect. The first one is all operations of a database must be completed and committed. If aborted, it will be rolled back and committed to the last consistent state. 2, No transactions can affect another transactions. This is called isolation level. Some kinds of failure that a database system can suffer is hardware fails, can suffer about system or transaction fail, a failure forced by the concurrency control, and a hard disk and disasters, hard disk failure and disasters. Some of them are controllable failures, but others are unpredictable, so we must pay attention for that. To control this kind of failures, the concurrency control keeps the transaction state, as the diagram shows here. Every transaction must be in one of these states. Must read-write operation. The read-write operation must always lead a transaction from an active state to another active state. When the transaction is complete, its state is changed to partially committed because it's not stored in the disk yet. To start the transaction, the transaction must persist the value by a commit operation. And if this failed, it aborts the transaction, changing its state to failed. The recovery system tries to roll back the operation, and the transaction changes its status to terminated. For each operation executed, this graph is checked by the concurrency control, and is checked every state of the transaction. This graph must be respected at all. If the database fails, the DBMS accesses the log file kept in the disk. No errors can affect the log file, except disasters or disk failure. The log file contains records of operation executed, necessarily the right operation. That's because the right operation must be undone in case of failure. The read operations, no need to undone a read operation. To allow the concurrency control manage the transactions, we can see that some properties must be granted for the transactions. These properties are called ACID properties or ACID properties. The first one is the atomicity that says that each transaction must be processed as a unit operation. It must be committed or fail and rolled back at the end. Consistency says that every transaction must leave the database in a consistent state. So it's a responsibility of the programmer, the database programmer, to grant that the consistency property will be okay. The third one is the isolation properties. It grants that no transaction will affect other transactions' result. This can be achieved by 4 levels of isolation that's shown in the presentation here. The level 3, for example, implements the repeatable read and the level 0, 1, and 2 that avoids the inconsistent analysis problem. The repeatable read avoids the analysis problem. The durability property, the last one, avoid all committed transactions to be undone. A transaction that has been committed must persist in the database until it's changed by another transaction. So only one transaction can change the data committed by another transaction. To handle with the transactions and the recoverability, the concurrency control creates some plans called schedules to execute the concurrent transactions. We can see that a schedule can be based on a recoverability, which will grant the recoverability of the plan, and based on the serializability, that is the order of the operations of transactions kept in a schedule, for example. Both analyses can be done in the plan, depending on how critical is the application that requested the transactions. A schedule S is the set of all operations in the transactions that is in order to execute. For example, we can see that the operation R means a read item operation, W means a write operation, If for further information, C means a commit and A an abort operations. The schedule helps to detect operations in conflicts. So we can ask, but when two operations are in conflict, what is a conflict? It must belong to a different transactions and access the same data item, and at least one of these operations are a write item. These are two operations in conflict. For example, read-read operations never are in conflict because they never take the database to any of the problems seen before. A write-read, a read-read, or a write-write pair of operations can cause a dirty read or an uncommitted update, for example. Therefore, they must be checked always before being executed or a transaction being committed. The perfect situation, of course, would be a complete plan. That's difficult to happen because the transaction control is always receiving new transactions requested by the applications. What's a complete schedule? A complete schedule occurs when all operations in S are the same in transactions and ends always with a commit or an abort, and the order of operation in S are the same in each transactions. The non-conflicting operation can change the order because they will not affect, for example, the result. We can change it. Sometimes even taking care of the transactions, for example, the concurrency control can abort a schedule for many reasons. That's why a schedule must be always recoverable, or at least must grant the recoverability of the schedule. A recoverable schedule is one that no problems can occur after after being committed. For example, there's no need to roll back. Okay? The non-recoverable plan cannot grant this clear execution, and a problem can occur, not necessarily, but forcing an abort and rollback operation if they occurs. A schedule, for example, is considered recoverable if it ends and commit only after all the transactions that have written the same item finished true. When there is a read operations of T1 after a write one of T2 over the same data item, we say that T1 is read by T2. I know this is difficult to comprehend. This condition is important to detect possible failure. We can see that T2 is read by T1 in this schedule here. In this case, T2 must commit only after T1 is committed, because if T2 commits and T1 aborts, we can see, then it must be necessary to abort T2 because of a dirty read. But if T2 was committed here, how can the database system could roll back the whole committed transaction? It's impossible. We will break the rule, the durability rule. Okay? We can see that this schedule here is recoverable. But just because the transaction T1 that we see here reads the item X written by T2 only ends after T2 has finished. Also, this schedule caused the lost update problem, but as the schedule is recoverable, the concurrency control in this case can reorder the operations and make a new equivalent schedule without causing the problem. By equivalent, we'll see here now for the next presentation. Another problem that frequently occurs is when a transaction that we call T1 that reads an item that was written by another transaction T2, you can see here. And it ends before the transaction T2 as shown in the schedule SB at the screen. In this case, if T2 aborts, it means that the value written by T2 and read by T1 is wrong and must be rolled back. It's okay to roll back transaction T2, but how can the recovery administrator can roll back a committed transaction T1? It break the rules again. It will break the durability property of this transaction. In this case, the schedule is not recoverable. This kind of rollback is called a cascade rollback, and it's good to be avoided. Not every cascade rollback causes a problem. Only if it has to undo, for example, in this case, a committed transaction. Okay, so that's the reason it's important to grant the schedules will be restricted. It means restricted the schedule. No transaction can read or write an item written by another transaction, T-line, before T-line takes effect. Restricted schedules are always recoverable, and it's easy to the BMS handle with it. That's why restricted schedules are important. To reorder some operations in the schedule, for example, the DBMS used the concept of serializability we talked before. That means the order of the operations and transactions in a schedule. The concurrency control, as necessary, can reorder the operation in a schedule without affecting the final result of the plan or the database consistency. A schedule is called serial schedule, a serial schedule, when all transaction occurs one after another, without being interleaved. It's a serial execution of the transactions. This is desirable, but it's not effective in terms of using resources. So some schedules must be built considering the possibility of end with the same results as a serial schedule. This schedule is called serializable schedule, and it is equivalent to a serial schedule, to a serial plan. Okay? But when two plans are equivalent, they are equivalent when their results are the same. But not all schedules that give the same result are equivalent. As we can see here, in this example, two transactions with the different operations that gives the same answer. So it's important for two equivalent schedules have the same operations in their transactions. That example, they were not with the same operations. If the schedule have a conflict, so we can say that they are conflict equivalent. But what's a conflict? A conflict occurs when the pair of operations, as we said before, read-write, read-read, and write-write, over the same item, appears in the schedule. In this case, the concurrency control can reorder the non-conflicting operation to achieve another non-conflicting equivalent plan. Not always, but it will pay attention to that. In the diagram here, we can see that the left serial schedule with its conflicting operations, and at the right an interleaved schedule with the same conflicts at the same order that we call a called conflict equivalent to a serial plan. They give the same answer. One is serial, another is interleaved. So to check if a plan is serializable, the concurrency control can build a priority graph with the transactions as nodes and the conflicting operations over the items as edges. If you build in the oriented graph and that forms a cyclic graph, so the schedule is not serializable. In this picture here, we can see that the bottom left graph is a cyclic one. So that plan cannot be serial equivalent, or there is a non-serial schedule equivalent to it. It's important to see that this cyclic operations. For example, there's another schedule here. Seems to be no serializable. But if we follow the line arrows using the labels as a guide, we can see that we cannot start and end in the same node following arrows with the same label. You can see here, it still have a cycle, but with different labels, which is not considered a conflict. Remember that it must be operations over the same data item to be in conflict. Therefore, we can see that the plan shown here is serializable, and there is a serial plan equivalent to it. So that's the end, and in the next lecture we will cover some aspects of the concurrency control, block protocols, deadlocks, and recovering algorithms. I ask you to don't forget to answer the online quiz for the extra bonus points. For the next class, concerning our flipped classroom, you must read the chapters 17 and 18 of the main book. It's the Navat book. And you must answer these questions that I will give here. Why the serializability, it's difficult, is a complex operation, and the database system cannot check entirely all schedules. It's new. A hint, it's about the complexity, the algorithm complexity. This will be for the next class, our flipped class. So, see you in the next class. Bye-bye.